All right, this is our last section of the notes for Unit 1, and we're going to title it Physical and Chemical Changes. Again, our overall guiding question for this unit is how do we classify the things around us? And the things around us can change their formation once in a while. They can change physically and they can change chemically. So understanding this concept is going to help us further classify the materials around us. Physical changes are defined as a change in which the form of the matter is altered, but when substance is not changed into another, so the substance stays the same. Now, phase changes are going to be an example of a physical change, and you're very familiar with phase changes. They're really nothing new. Ice melting or water freezing are both examples of phase changes, and we've seen this. Now, in chemistry, we're going to deal a lot with chemical equations, and you may have seen them in the past, especially if you've done any work with the iQuest curriculum in middle school. But this might be the first chemical equation you've seen in a while. So typically we've got what you call a reactant side that's over here on the left, and a product side that's over here on the right. And those two things are separated by what's called a yield zero. And that yield zero is typically pointing in only one direction. Usually it's pointing to the right. However, in a phase change, we can have a solid turn into a liquid, and then if we drop the temperature, that liquid can turn back into a solid. So in this case, we actually have a double-headed arrow, as you can see, that just shows that this reaction can go back and forth, and this phase change can go back and forth. One other thing that you're going to notice within this little terminology, or the little diagram that you have right there, is the S and the L, and I bet you can probably figure out what those mean. The S stands for solid, and the L stands for liquid. One thing you'll notice in this equation is that the molecule stays the same, both on the left side and the right side. And if the molecule stays the same, we define this as being a physical change and actually not a chemical change. All right. The other half of the phase change cycle is the condensation or the evaporation of water into gas, or of gas into water. We can write a very similar looking equation. Looks like this. H2O in the gaseous form can give us H2O in the liquid form, or vice versa, again with that double-headed arrow there. And if we look at this at a particle level, if we actually want to see what's going on here, and why this is not a chemical change, it's because the particle that's involved, which is the water molecule, stays the same throughout the entire process. So as you can see, if it starts out as ice here on the far left, which would be this guy right here, you see the molecule's got one single red attached to two whites, okay, and that's the molecule itself. And they're all kind of hanging out with each other very close. As water melts, actually the neat little crystalline structure actually breaks, and now you have this very random looking action here in the middle, and that's liquid water right there. But as you'll notice, every single particle in there is still the water molecule, one red, two whites. If we heat up the substance even more, then we're going to get the last phase, which is the water vapor phase. And again, every particle is the same, one red, two whites, but now they're much further apart, and that's the gaseous state. You can see that we can reverse that. We can then cool down the water vapor to get water, and cool down it again to get ice. And all along this process, the water molecule never changes. It always stays the same. All right, another type of physical change that we want to talk about is dissolving. So when we dissolve salt into water or sugar into water, like I did for our sugar solution calibration curve, this is not known as a chemical change. This is actually a physical change. And one reason why we can think of it that way is because the substance itself can be returned to its original state by evaporation. So we can go from salt into water. The salt appears to disappear, but then if we boil the water off, we can get the salt back. We can reclaim the salt. And that's a pretty simple process. So in this process, the salt doesn't actually physically change, or chemically change rather. It physically changes, but it doesn't chemically change. So we can write another form of an equation here with the salt, which is sodium chloride. You'll notice the S again stands for solid, changing into sodium chloride. And now we have a new symbol down here. And that new symbol, the AQ symbol, which you can see right there, stands for aqueous. That means that that particular substance has been dissolved into water. And we know that when we dissolve salt in the water, it disappears more or less. We can't see it anymore. But if we were to drink the water, we could certainly tell that it was still there. Here's a nice little particle diagram. It's a little bit involved, I might say, but it really shows this concept of the fact that you've got the salt in this crystalline structure here on the far left, and then it's introduced to the water molecules. The water molecules are all of these guys. And then what happens is the salt starts to break apart, okay, into its individual, what we call them ions. So this is chlorine, and this is sodium right there. And as that process continues, maybe we stir the solution, we get further breaking apart, and eventually all of the salt crystals appear to disappear. And so this is our resultant. Now, I ask you, could we reverse this quite simply? Yeah, all we'd have to do is toss a little bit of heat underneath. All right, so toss a little bit of heat underneath there, and we could actually get this process to run in reverse, where those crystals would reform, and we would get salt again on the bottom of our dishpan. If you're confused by this, just go ahead and try it at home. Take some water and put a little salt in it and boil it on the stove, and very carefully watch it, okay, so that you get to the end, you don't boil all the water off, but most of the water, and you'll notice that there's a white film that starts to form on your saucepan, and that's the salt being reclaimed. So those are physical changes. Phase changes and dissolving being the most common two. So what if it's not a physical change? What are the other types of changes? The other types of changes are called chemical changes. Chemical changes are just simply defined as a change that results in the formation of new chemical substances. In essence, the elements that you're playing with rearrange. So it's like taking, building a house out of Legos. Okay, you build a house, a beautiful house out of Legos, and then you take every single one of those Legos and you demolish the house, and then you build a dinosaur. Okay, so you're using the same building blocks, but you're ending up with a different product, and that's a chemical change. Okay, it'd be very difficult to get the original material back. So if I'd have to break apart the dinosaur and get the house back, maybe without instructions, it'd be pretty difficult to do that. Okay, so I've got a particle level diagram again showing this. So this would be like what happens if you've got a gas stove at home, or your furnace, if your furnace is a gas furnace, if you don't have a wood pellet stove, or a Bunsen burners here in class. We use a gas called methane, and that's this stuff right here. It's called methane, or carbon tetrahydride, right there, CH4. And it combines with the oxygen in the air. And as you see, the particles, they rearrange, they mix up. And so we get new things, we get products. Now, one of the big things that you'll notice with this chemical equation is that the arrow now is only pointing in one direction. Now, you'll learn later on when you take more and more chemistry that there's something called equilibrium, and this arrow can in fact point in both directions. But I'll tell you what, for the most part, this reaction, this chemical reaction, is always going to be driven to the right. Meaning that if we've got some methane and some oxygen and we light a spark, we're going to get that CO2 and that water to be produced. Now, this would be very, very difficult to get it to reverse. And just think about it this way. I mean, could you go home and light your stove and capture all the gases and put them in a bag and then get the original oxygen and methane back? That'd be difficult. Could we do it? Sure, but it wouldn't be too easy. So that's really the big difference between a physical and a chemical change. Physical changes, we can reverse them easily. We can get the original stuff easily. In chemical changes, we cannot.